Hi everybody, welcome back to Chem 140. Let me just wind this down here. What do we got going on today? I'm going to finish the last of Chapter 3, which is like 2 slides. We were out of time yesterday, so we didn't get that done. But then we're going to move on to Units 4 and 5. Units 4 and 5 are like one section each, so I just pair them together. So we're going to sort of do a little grab bag of stuff today, where we talk about density, which is more or less Unit 3 continued. And we're going to talk a little bit about temperature, which is more or less things that you probably already know, but just in case you aren't. And then finally, next week, we're actually going to do chemistry. So we've done the prerequisite math stuff. We'll finish that all today. Agenda items down at the bottom. So if you have not done quiz number 1, too late. It is closed. I will go release scores after this lecture. If you have not finished lab worksheet number 1, it's due tonight, and then it will close tomorrow. So make sure you get that in by the deadline. I know some students have been emailing me about how to access the Google Sheet or like what to do for the lab. Make sure you are watching the lab video. We had a whole 30-minute thing dedicated to how to do the labs, how to access the worksheet. Again, do not ask me for permission to edit the worksheet. I will delete the email because I told you not to do that. Okay? All right. If you have any other questions, let me know. Otherwise, we're going to get started. So we got percent error on the board here. Percent error is a rubric that is used in the laboratory to determine how close you are to the correct answer. Okay, so I'm going to say, for just the sake of argument, that the correct answer... Oh, nothing... Oh, there we go. Okay, I didn't click on the screen. Let's say the correct answer was 2.5000. And you're doing an experiment, and you measure... We'll call this trial 1. You measured this. And they could be centimeters or milliliters or whatever. And so what we would do to figure out what percent you were off by is we would follow this formula. You do measured minus true divided by true. So for trial 1, we would say 3.0000 minus 2.5. I don't know why I put all these zeros now, but that's okay. And I need a calculator, not my phone. When putting this in your calculator, make sure you're putting in abundant parentheses. And so when I do this, I get 0.5000 divided by... Well, I guess we'll just write it out so that you can see the sig figs here. And that's our answer. And the reason that this is our answer is because this number right here, this 100%, is exact. This is 4 sig figs, and this is 5 sig figs. So our answer should have 4 sig figs. All right, how far off was I? I had a difference of 0.5. So this number and this number were off by 0.5 in this case. Now what I'm going to do is I'm going to do trial 2 here. And I'm going to be off by 0.5, but I'm going to be in the opposite direction. And this is how the... Oops, that's not what I meant to do. This is how the problem changes. So this number is going to be different. And then all this is different. Unfortunately, I can't like select and erase. So when I do this now, 2.0000 minus 2.5000 is negative 0.50000. And when you do the math, you get the same result that you get before, but there's this minus sign on the front, right? So what do we conclude about doing this? You get the same number if you're off by the same amount from the correct answer. But depending on the direction you're off by, you get a different symbol. So if you get for percent error, if you get a negative percent error, that means that your measured answer is smaller than the true value. But if you get a positive, then the measured is bigger. Now, some textbooks have this done to it, where they just say, oh, we're going to take the absolute value. Then we don't have to worry about this down here. But then you lose information. So I recommend that you don't take the absolute value, and you just recognize what the symbology means in terms of the sign. If you get a negative result, don't panic. Don't say, oh, it's negative, what do I do? Well, if it's negative, it just means it's less than 0, right? It's the same displacement from 0, just to the left. So if you get a negative percent error, your answer is smaller than what it should have been. If you get a positive percent error, your answer is bigger than what it should have been. So keep the sign, I say, and do percent error using all of the rules for sig figs that you've seen so far. Now, again, you're going to have a... Oops, I didn't mean to put that on there. You're going to have a subtraction part, so you got to do the subtraction sig figs rules before you do the division one, so be careful. All right, so we're going to do this example here. If I have a density of aluminum experiment and I measure it to be 2.63 grams per cubic centimeter, but it was actually 2.71 grams per cubic centimeter, what is my percent error? So let's do that calculation. And again, the trick is going to be, where do the sig figs fall out here? Let me zoom this in, actually. All right, so my measured value was 2.63 grams per cubic centimeter. We're going to talk about what that unit means in a little bit when we talk about density. Now, the true value was 2.71 grams per cubic centimeter. So let's apply the percent error formula. Measured minus true divided by true times 100%. We're just going to plug in the numbers. So my measured number was 2.63 grams per cubic centimeter. My true value was 2.71. And again, the true value is the same thing. And so I have to do this operation on the top first. So that means I got to do subtraction. Now, subtracting like this is kind of weird, right? Like, we can do vertical subtraction, but we can only do it if the bigger number's on top, yeah? So what I do in this case is, if you're subtracting a larger number from a smaller number, is I put the negative up here, and then I treat it like subtraction. And it's just that my answer will be negative. Okay, so that's just a little shortcut. If you're having to do this on your or not on your calculator, by paper, and you're like, well, I can't subtract that way, we'll just invert the order and then make the answer negative, and it'll work out. So this is the result of this calculation right here, and you'll notice that it only has one sig fig, so that's going to affect our result. So it's very important to do the subtraction first. So now we have 0.08 negative grams per cubic centimeter divided by 2.71 grams per cubic centimeter. I forgot my times 100 up here. 100%. My units now cancel, and I just punch it in the calculator. So I get negative 0.08 divided by 2.71 times 100%. And what I get is negative 2.952, but we already said, oh, there's only going to be one sig fig here. So I would report my percent error as negative 3 due to sig figs here. So, oops, I have a cord on the tablet here. So again, this is one sig fig. Oops, wrong color. Can I undo twice, or is it going to yell at me? It's just going to do that. So again, I have one sig fig here. This is 3 sig figs, and this is exact. So my answer should have one sig fig. There you go. That's how you do percent error. Now, why is our precision on our percent error so bad? Like, why did we lose all of our sig figs but one? So again, one, it's because of our subtraction here. But two, these numbers are really close to each other, right? As your precision increases, your error decreases, and it gets harder and harder to identify your error to an appreciable degree of precision. So since this is dealing with error, and it's hard to find our error because it's so small, we're going to have very few sig figs. Okay? Very few sig figs in the error, I should say. All right, so I'm going to give you one of these to try now. So I have what's called a standard sample here. And a standard sample is basically an example, or not an example, a experiment that has been standardized. You should get the same result every time because we have chosen a set of circumstances and controls that require that outcome. And so 3 students are doing an experiment to determine the amount of oxygen in a standard sample. And that standard might be like, I gave you 5 grams of this compound. And so it's all been precisely measured, and I put it in a vial, and I gave it to you. And 3 students did a reaction to get oxygen out of it, and these are the masses that they got. Then the laboratory technician who prepared all of the stuff and does all of the bookwork for like what's in the samples, he does the experiment, or she does the experiment, or they do the experiment, or whatever. And the standard amount that they acquire is 2.705 grams. So what I want you to do is for student A, B, and C, if the true value is what the laboratory technician got down here, determine student A, B, C's percent error individually. Okay? Be careful because notice that I have all sorts of crazy sig figs things going on here. And so all of your answers may have a different number of sig figs. Okay? So this is just practice on more sig figs. Okay? Go ahead and do these examples. I'll come back to you in 5 minutes. Ask me a question in the chat if you have any questions, and we'll go over the answers together when I return. See you in a bit. Hi, I'm here. Just let me know if your audio is working. I'm giving students a few minutes to work on the problems. One or two more minutes, and we'll go over the answers. All right, let's go over these answers together. First, let me clear my screen here so that when I do that, you can actually see, well, nothing, I guess. All right, hopefully that's not too small. All right, so we are going to, first let's write down the percent error formula. There we go. So student A's value, so there's student A, 2.725 grams. We'll subtract the true value, 2.705 grams, divided by the true value times 100%. And so we'll do our subtraction vertically over here. And you can see that student A was pretty close for his result. And so when I multiply all those together, well, divide, I guess. 020 over 2.705 times 100%, I get 0.7393, which this number right here only has 2 sig figs. So my result should also have 2 sig figs. 0.74%. That's the answer you should report. Note that there's 2 sig figs because the 0 is a sig fig. It is known. All right, let's look at B here. And what we're going to do is we're going to go like this. Oops, that's not what we're going to do at all. It's the power of Photoshop. And then I could just paste. And nothing happened. Oh, that's why. There we go. And this is where I wonder, oh, is it going to paste the email I sent Samita because I wrote it in some other field or something and then I had to like reply to a different, I don't know, I had to copy and paste it. So for B, we have 2.510 minus 2.705 divided by 2.705. So we'll set up our subtraction vertically. Now the bigger one is the second number, so I'm going to do it like this. And then just make my answer negative. 5, 9, 1. Yeah, that looks good. So I'll take my answer, divide by the true value, times 100%. Oh, my units should be canceling out. I just haven't been saying that. And what does the calculator give me? Negative 0.195 divided by 2.705 times 100. Negative set. Oh, first of all, how many sig figs should I be writing down? Well, there's 3 here. So negative 7.21 is what I got. And then finally for problem C, if I paste, I was just going to stick it in the middle there. Boop. Same thing. So let's see here. So this is subtraction 9, 0. Uh-oh, ran out of space. So grams cancel. And when I do that, I should have 2 sig figs. I got 3.5%. There you go. All right, hopefully that's what everybody got. Let me know if you have any questions about those. That's it for Unit 3. Finally, right? Like, we've been doing it forever, it feels like. All right, so let's go over there. Let me hit the button. Oh, there will be sound for this, so I might as well do that. And then hooray. Hooray! All right, your screen will go black for just a second while I load up Unit 4. Do I have the folder open already? I do. So that's Units 4 and 5. We don't need Unit 3 anymore. Yeah, there we go. Boop. And that should appear. There it is. Okay. So you can see why Units 4 and 5 go together. They're very short. In fact, how many slides total is this? 11. We're not going to do that much. We're probably going to finish Unit 4 before the break, and then we'll do Unit 5 after, and then we'll do our Q&A if anybody has any questions that they want. All right. Unit 4 is about density. Density is really just a special ratio that we've decided has relevance for various applications. For example, the density of an object is how much stuff is contained within a specific amount of volume. The more stuff that you put in there, that is, the more atoms or matter, however you want to define it, the higher its density. Now, if I asked you which was heavier, a pound of feathers or a pound of bricks, you would say, well, haha, joke's on you. They're both a pound. They weigh the same, right? But then if I asked you which one was more dense, you would actually have an answer for me. You'd say, oh, the bricks are more dense because they're heavier, bulkier things in a smaller space than the feathers. But a lot of people mix up heavier with denser. So just be mindful of that. Density is a fixed intrinsic number, whereas how heavy something is just how much of it you have. All right. We're going to represent density as the ratio of mass to volume, and we're going to put units for mass in the spot on the top and units for volume on the bottom. Typically speaking, we're going to be using grams for this class. Most solids are identified in grams per cubic centimeter. You may also see other textbooks use kilograms per liter or kilograms per cubic meter. They're all valid, but for our purposes in this class, if we're working with a solid, this is the density that we're going to be using. Now, other phases exist. If we have a liquid, we're going to be using grams per milliliter. And the reason that we change from cubic centimeters to milliliters, because even though they're the same thing, milliliters are much easier to measure for a liquid. You just pour in a graduated cylinder, yeah? And then for a gas, we change from grams to milliliter up to grams per liter because gases are really light. So with a gas, it's hard to get a gram of stuff without getting a lot of it. And it turns out that by the time you get gases that are roughly the mass of 1 gram, you need about a liter of it. So those are our units. Those are going to be the norms that we're going to use in this class. If you're looking up densities on Google, be careful that you look at what the units are, because oftentimes Google will give you units in like kilograms per liter or milligrams per deciliter, depending on what you're looking at. Density can be used in all sorts of different ways, but it's always going to be some sort of mass over some sort of volume. And there's really no global standard. There's just the chemical standard that we deal with in chemistry. Okay, so because Google is not tailored for chemists, be mindful of that whenever you're looking stuff up on Google. Now, if you mix things together and they have different densities, the things with the highest density sink to the bottom, and the things with the lowest density will float to the top. So what we're going to do is I'm going to show you this video. We all know how well that worked last time I did a video here. Hold on, I'm hitting stop at the top of my browser bar, like that's going to stop a YouTube video. That probably just stopped, like, putting comments on the screen or whatever, which is fine. You should never read the comments. Okay, so window capture, density tower. Boop. That's a little big. Hold on. All right. We don't really care about the music on this because it's just this goofy little, like, ditty. And I don't want to give YouTube another reason to copyright strike me. So, all right. So we're going to put all these things in this tower. And it's going to list them on the screen. Oh, these are the materials to help with it, but the liquids are going in the tower. You do not need adult supervision. Oops. I'm going to pause right here. There we go. These are the liquids that are going to go in the density tower, and they have been arranged from the most dense on the left, that's honey, to the least dense on the right, which is lamp oil or kerosene. Yeah, this is a common experiment that we do in grade school because it's just fun. And you can actually do this at home, but the trick to making the column actually work and not just making a mess is that when you have to alternate your substances based on their ability to mix. So, for example, honey and corn syrup will mix, but they're so viscous that they don't do it unless you force them to. Whereas rubbing alcohol and lamp oil don't mix well at all. They form a separate layer. Same with water and vegetable oil. So we've actually chosen these liquids very specifically so that any two that would mix with each other very well, they're isolated by things that won't mix. So for instance, water here will mix with rubbing alcohol and form one layer, but we put the vegetable oil between it so it doesn't do that. And you're going to see this when they're putting these things in the column here. The first few you just sort of plop in, and then after that you have to go very slowly because you don't want them to mix. And then pouring down the side is just because it's even slower. And then once you've done all the liquids, you can drop all the objects. And you'll notice that they kind of float. But then they stop at certain spots. Like the tomato went like halfway down. And there you go. This is where all of our objects sorted in our density column. So the bolt, which is made of metal, is going to be far more dense than any substance in this column, and it falls straight to the bottom. The other objects sort based on which two layers their density falls between. So, for instance, tomatoes, like most vegetables, are mostly water, right? But there's other stuff in there. So it makes sense that their density would be a little bit higher than water for like the fibrous material and the cell walls and stuff like that. But not so much that it is so dense that it would fall down several layers. So its position makes sense. A ping pong ball is mostly air. So even if you try to submerge that, it will just pop right back up to the surface because its density is very low. It's just mostly air. And then all the other things are ranged by their density. So you could see those in here. And so yeah, that's a density column. So this is a universal truth that when you mix things together, they sort by density. And this is actually the premise by how shipbuilding works. So if you have a boat, so here's my boat, and we'll put like a, I don't know. Now I'm just being too artistic with it. There we go. So there's my boat, and then here's the water level. And so this is the ocean, we'll say. And the density of ocean water is about 1.1 grams per cubic centimeter. Now, I did say we were going to use milliliters for that, but I'm going straight to a boat, which is going to have the same unit anyway. In order for our boat to float, its density must be less than the density of the ocean. So, in order to make a boat float, you just have to limit the amount of mass you put on it. Or, and this seems counterintuitive, but it totally works, you make the boat bigger. So you can make boats very, very, very large, provided that you don't exceed a maximum mass that would cause its overall density to be greater than that of the ocean water. Now, if your boat springs a leak, oops, I didn't mean to go forward here. If your boat springs a leak and then fills with water, then the density of the boat would be more than that of the ocean because you've got the water plus all the other stuff, and then the boat sinks. So, naval stuff, naval navigation or nautical navigation, I don't know what two words I'm trying to string together. It's all based on density. All right, so I'm going to give you a very simple density column, and what I want you to do is tell me which of these floats. The olive oil that has these properties or the water that has these properties. You may have already done an experiment like this, like just cooking in the kitchen with Italian dressing for your salad or whatever. But based on the numbers that I've given you here, tell me which one will float when you mix them together, and then why. Tell me why. You have to support it with data, okay? I'll give you 2 or 3 minutes to do that, and then we'll go over the answers in just a second. One more minute, and we'll go over the answer. All right, so this is very straightforward if we have the formula for density. So the formula for density is mass over volume. So for the oil, we've got 18.6 grams divided by 20 milliliters. And that is, it's less than 1. 0.930 grams per milliliter. Now you'll notice that the units don't cancel out. We keep them both. And then for the water, we have the same mass and the same volume. And because the oil has a lower density than the water, the oil will float on top of the water. If you've seen an oil spill, for example, the one that happened at Huntington Beach, which was the beach I used to go to when I went to UC Irvine, so that's kind of hits close to home. I also have family in Huntington Beach. There was an oil spill there just off the coast of Southern California, and all the oil got on the beach. And it's going to take months to clean all of that up. And I honestly don't know how you do that. You can't wash it away. Where would you wash it to? You can't wash it back in the ocean. But what does the oil do? Well, the reason that oil slicks are such an issue is because they form a slick on the surface of the water. They float to the top because their density is lower than that of water. And that's true of most oils and most fat containing substances. They don't have a very high density. And we talk a little bit more about that in biology and biochem. Why is the density of lipids so low? And it has to do with their structure. So if you're taking biology, you'll get to learn all about that in biochem, which is like this, but with bio. All right. Let's do some more examples here with density before we take our break. Now, using the density formula, I have constructed a problem that has a mess of units here. So this is the density of ice. Ice has a density of 0.9167 grams per cubic centimeter at 0 degrees Celsius. Now, you don't need to worry about the temperature. It's just that's when ice forms, right? If a glacier has this volume, how much mass will it have? And so I'm going to leave the answer to be whatever units you want them to be for mass. Now, obviously, you have to give me a mass. If you gave me some other, if you said it was 7,000 kilometers, I'd be like, well, that's not a mass. That can't be the answer. But if I don't specify what the units are, turn them into whatever units you want to. Usually, that's me implying if you give me grams or kilograms, I will take either of those answers. That's fine. But like, don't convert it to like penny weight or barley corn or something stupid. All right, so I'm gonna leave you to try this for a few minutes. Be very careful with your units, though, and we'll go over a solution in just a bit. All right, one more minute. We'll go over the answer. All right, so... Oh, I was making new layers on my Photoshop. Hold on. Layer 2, delete. Blah. Layer 1, delete. Blah. Delete all. There we go. All right, so you'll notice that for this problem, we have all sorts of crazy units, and none of them match, because of course they don't. So let's start by writing down the density formula. And I know that the density of the ice is 0.9167 grams per cubic centimeter. And I know that the volume is 35,720 liters. Well, if I'm going to get a density in units of cubic centimeters, and I get the density by dividing mass and volume, I should make these two match, right? So what I'm going to do is I'm going to turn this into cubic centimeters. Well, you can do that by going from liters to milliliters. And then remember that milliliter and cubic centimeter are the same thing. So then we can do the numbers. That's an easy one to do. And then this is just 10 to the minus 3. And then that would be that many milliliters. Oops, not milliliters. Sorry, we canceled that. All right, so that would be the volume in cubic centimeters. If I did my math right. 1, 2, 3, 4, 5, 6. Yeah, that should be okay. And so now we're going to go up here to my formula. I know what the volume is because that's right here. I know what the density is, that's right here. So I just got to solve for the mass, right? Now, I would encourage you, whenever you're doing these types of problems, don't just plug in the numbers. Solve for the variable that you're doing first. So we're going to solve for m. I'm going to multiply both sides by v to cancel it out. And then my formula would become the mass is equal to the density times the volume, which would equal 0.9167 grams per cubic centimeter times this crazy number of cubic centimeters. And you'll notice that the volumes units cancel out, leaving only grams, so that when I do this, I will get an answer that's in grams, which I'm not going to turn into pounds, because pounds are a silly British thing. They liked it so much they made it their money. And I get 3.274 times 10 to the 7 grams. And yeah, if you divide my answer by 400, I think it's 454, you should get your answer in pounds. In fact, if I do it on the calculator, I get 72,000 something. Yeah, it's close enough. 453 point something. I don't know. All right, so there's the mass of our glacier in grams. If you did it in kilograms, it'd be 10 to the 4. If you did it in megagrams, for some reason, it'd be 10 to the 1. And if you did it in nanograms, well, good for you. We're going to take a break. When we come back, we're going to do the next problem on the slide. There's a few more density problems to do. Then we'll talk about temperature. Temperature is not going to take that long. We do need a timer. So there's that. And we need more Stardew Valley. I mean, it's autumn. Why don't we play autumn songs if I can pause this in time? There we go. I didn't. That's okay. I'm going to find the best track in the game. Where is it? Ah, there it is. Alright, we're back. Alright, so we did the first problem here. And I need to get the answer on the screen here. Here's the second problem. That's more or less the same type of problem. It's just you got to figure out what to do with the units here. So if I give you a sample of air that has volume 32 kilograms and its density is 1.29 grams per liter, what volume is that? Or what volume did I give you? Will the quizzes be graded? I have to hit a button, and then they will release the scores. I have already graded them, but I did want to make sure I got them all in, and they closed at midnight last night, and I wasn't up in time for that. So I'll attend to that after class today. Go ahead and try this problem. I'll give you about 5 minutes to play around the units. Now, notice I asked for a volume. You can give me any volume you want to, but you should probably pick something like liters or milliliters, because those are the common ones. Work smarter, not harder, right? All right, I'll see you in a bit. One more minute, we'll go over the answers. All right, so let me set this up here. So for this problem, yeah, I definitely have audio out, so if you can't hear me, double check your settings. I should probably type that since you can't hear me. I am definitely talking. Hopefully people can hear me. It says that they can, question mark. Okay. Anyway, we're going to do this problem. Oh, I didn't capture the correct problem, though. There we go. You can hear me. Okay, good. Can you hear me now? Good. Yeah, that was like one of the first memes was "Can you hear me now?" Good. It was for like Verizon or something. Okay, great. So we'll start with the formula again. And I know that the density is 1.29 grams per liter, which I'm going to rate like that for no reason at all. And the mass is 32 kilograms. Now, obviously, those units don't match up, but because I'm going to be throwing in the density formula, I might as well make them match. So what I'm going to do is I'm going to turn this kilogram into grams, just because that's trivial enough to do. So those would cancel out. And by doing that, I have... Oops, I gotta do this in scientific notation, don't I? 1, 2, 3, 4. I have this many grams. So there's my mass. It's the mass of air in my sample. And I want to find what volume that is. So I need to solve for volume here. So if I multiply both sides by V, they cancel out. And then I would divide both sides by D. So once I'm here, I would do that. So that now I have volume equals mass over density. And so now I'm just going to plug in the numbers. So for mass right here, I'm going to put in the number of grams that I have. And then for density, I'm going to put the density. 1.29 grams per liter. Now, that's kind of an awkward place to put our unit, right? Because I have a unit that's a fraction, and it's on the bottom of a fraction. Well, remember what happens if I have a fraction divided by a fraction. That's like multiplying by the reciprocal, right? So these two things are the same. So if I take the fractional thing and make it a reciprocal and multiply by that, I get the same result. So I'm going to take that over here. And I'm just going to take my units and do that. And so that will be the number of liters of air that I have. It is 3.20 times 10 to the 4 divided by 1.29. And I get 24,806, which should be 3 sig figs. 24,800 liters. So to get a kilogram or 32 kilograms of air, you need 20,000 plus liters of air, which sounds absurd, but air is very light. You need a lot of air, a large volume, to get any mass at all. There you go. So those are some actions and operations that you can perform with the density equation. So I have a few last examples for you to try here. How do you finally get mass of gases less dense than air? So you treat it the same way. However, we would have to use isolated or pure samples. We're going to talk about pure samples versus mixtures later on. Air is a mixture. So, like, air has oxygen and nitrogen in it and all sorts of other things in it, like water vapor and carbon dioxide, argon, etc. But if you wanted to find the mass of gas of, say, just like nitrogen, you'd have to distill out the nitrogen and get it by itself. We're going to talk a little bit about that in Unit 6, actually. So that's going to be the next thing that we do on Monday. All right. 3 more density problems for you to try. Go ahead and do these. We'll go over the answers in about 6 or 7 minutes. I am going to hit mute again, so don't panic. I don't talk while you guys are working because I want to give you time to practice. So try these 3 problems. We'll go over the answers together in a bit. See you in a bit. Few more minutes. We'll do 2-3 more minutes, and we'll go over the answers. All right, let's go over these 3 problems here, and then we'll be done with density. I think this is the last slide for that. I gotta make sure I'm actually on Photoshop when I'm trying to clear this. Otherwise, it'll be like, oh, everything is gone. And that would be bad. Oh, my cat is meowing. Yeah, I get it. You're bored. He's gonna sit here and just meow in the background or something. All right. If a gold bar with mass 329 grams was melted, what volume would it occupy? So we know that the density of gold is 19.3 grams per cubic centimeter. And we know that its mass is 329 grams. And I want to solve for the volume. And we saw me do that before. There's the formula that we would get. So we've got this going on, which again we can then write by taking the reciprocal of my units there. And the volume that I get in cubic centimeters is 329. Oops, calculator's not on. Divided by 19.3 is 17.0 cubic centimeters. All right, good. All right. What is the density of this beverage? So this time I know the mass and the volume, so I can just plug them straight into the density formula, right? So here's the mass. Here's the volume. And we'll just do that. And that's very straightforward. And I got 1.02 grams per milliliter. And I ran out of space because I didn't scroll all the way to the top. I'm going to leave that on the screen in case you want to pause the video to look at it. And then we'll go all the way back to the top here. And then for the third one, I give you its volume, and we need to know what mass the ship can have. So we're going to be solving for mass. And I know that the volume is 6. Is that 65 or 6.5? I can't see on that screen. Give me a second. 65. So 65 times 10 to the 6. And that's in liters. And the density of the water that we're looking at is 1 gram per liter, or milliliter. Now, we need these units to match. So I'm going to just do this. And you should be able to do that calculation on your own by now. Just to save space, because I'm kind of short on space here. So I'm going to take the mass to be the density times the volume. So the density is 1 gram per milliliter times the volume of the ship, which is 65 times 10 to the 9 milliliters, which would be 65 times 10 to the 9 grams of ship. Or more appropriately, it'd be 6.5 times 10 to the 10 grams, or whatever. However you want to represent those units. All right, if you have any questions about density, let me know. That is the density section. Let's talk very briefly about temperature. We're not going to do the temperature exercises because it's literally addition and subtraction. Times 10, did I write the wrong number? Oh, so it's times 10 to the 9. And the reason for that is because the volume is in liters. So it's 10 to the 6 here when it's in liters, but to make it milliliters, you get more of them. And since it's grams per milliliter and not grams per liter, our answer should be times 10 to the 9. If other questions come up about that, let me know. All right, let's talk about temperature. All right. So this is my temperature slide that I like to give. So there are 3 units for temperature conversion that we're going to care about in this class. And of those 3, one of them we don't care about at all. It's just there for us to make fun of. This is Fahrenheit. Fahrenheit is dumb. someone decided that they were going to set reference points to 32 and 212. The freezing point of water and the boiling point of water, let's just pick these random sounding numbers. And then let's have a whole nation of 300 million people use them. So now, whenever I use Fahrenheit around the rest of the world, they're like, what the bloody hell's this? What do you mean it's 100 out? How do you not dying? That's my Cockney Australian New Zealander or something. I don't know. I'm trying to offend as many cultures as possible. Fahrenheit is garbo. It's stupid, and we should feel stupid for using it. So we're not going to use it. Celsius, on the other hand, is very useful, but it does have one fatal flaw. The good part about Celsius is that the numbers that we use for these reference points are much easier to remember. They're 0 and 100. And there's only 100 spaces between 0 and 100, whereas over here there's 180. So 1.8 Fahrenheit equals 1 Celsius, which is stupid also. So why would you even want to deal with Fahrenheit? I don't know. Now, the issue that comes up with Celsius is that there's a 0 value at a reasonable, and by reasonable I mean you can access it, temperature. You can go outside and have fun in the snow when it's 0 degrees out. That's totally a thing that can happen. You can also do science at 0 degrees. Now, let's suppose you had a formula like this that involved temperature, and you rearrange the formula to solve for something, and then you had to input 0 degrees Celsius into the formula. Well, that's not going to work, right? You cannot use 0 as a denominator. When you do that, your number explodes. You get an undefined result. So it doesn't make sense to have a formula that only works in certain numbers around that are far away from this perfectly reasonable temperature to have. So what we instead developed is we said, okay, can we get that 0 somewhere else? Maybe, say, at the bottom of the scale, down here. And that's where the Kelvin scale comes in. The Kelvin scale is what's known as the absolute scale, and we use Kelvin in calculations. And the whole reason that Kelvin exists is because we can't use Celsius. Otherwise, Kelvin and Celsius are the same thing. You could see that 100 Kelvin is what separates the freezing point of water from the boiling point of water. Now, the unfortunate part of this is that because we set the 0 point elsewhere, everything else kind of falls on the scale where it does. And it turns out that for Kelvin, the freezing point of water ends up at 273.15. Oh, excuse me. Talking about temperature is boring. And the boiling point falls at 373.15. So those numbers obviously don't commit those to memory. But you'll be working with Kelvin enough that you'll probably remember them anyway. And so that's the 3 temperature scales. Now, there is a 4th temperature scale that's like the Kelvin equivalent for Fahrenheit. And it goes right here. But it needs a letter. And I was wondering if you could figure out what letter goes in that spot. That would be thematically appropriate. Now, if anybody has any guesses, I'd like to hear it. I'm glad that somebody got the joke. But it's not you. Oops, I'm clicked on the wrong thing here. It's not you. So it is the Rankine scale. That's my temperature slide. So the Rankine scale is exactly the same as the Fahrenheit scale. So this is just trivia at this point. So there's 180 degrees Rankine in this interval, but we have set the bottom of the temperature scale to be 0. Now, on the next slide, we're going to talk about what that means. What is the bottom of the temperature scale? Is there a top of the temperature scale? Can you increase temperature forever? Turns out you can. But we have defined temperature in a very specific way. Oh, do I have that slide on here? There we go. I'll show you the formulas in a second again. We have defined temperature in the following manner. The temperature of something is related to how fast the molecules in that something are moving or vibrating or translating or whatever. So if I have a sample and the molecules are perfectly still, then we would say that there is no molecular motion. So perfectly still has no molecular motion to it, and therefore that would be 0 Kelvin. And so we call this absolute zero, and you've probably heard of that expression before. Absolute zero is the lowest theoretical temperature when we define temperature this way. If temperature is just how fast things are moving and how much kinetic energy they have, if there's no movement, there's no temperature, and we'll call that 0. Now, that is a theoretical temperature. It's not a practical, this is something we can easily reach temperature. Because if you have something that has no molecular motion, in order to keep it that way, you'd have to insulate it from the universe, and there's no perfect insulator, so eventually some heat would transmit through the insulator and would then be absorbed by the stuff that is at 0 degrees Kelvin, and then it would no longer be at 0 degrees Kelvin. Now I'm going to remove this on the screen real quick here. Just as a fun factoid, the temperature of outer space, on average, is about 4 Kelvin. Would that occur if the universe died of heat death? Get back to me when the universe dies of heat death, and I'll be able to answer that for you. I have no idea, though. This is the average temperature in the universe, 4 Kelvin. Obviously, it's hotter in some places, and it must be colder in other places. Now, the lowest temperature that we have ever gotten to is about this. Something like this. And this is in a lab in Switzerland. I think it might be CERN. I'm not sure. So what that means is that the coldest place in the known universe is in Switzerland. That's cool. I've always wanted to go to the Alps because it's cold. I don't know. These are the formulas for converting between temperature. These are not worth memorizing. But what is worth noting is that everything in the Fahrenheit Celsius formulas is exact. So if you're using sig figs, which you, of course you are, when you're adding 32, this is exactly 32. Or if this is subtracting 32, it's exactly. These are exact numbers too, 1.8. Everything in here is exact. This number right here, however, is approximate. So if you're using the Kelvin formula and you have a temperature that goes to the thousandths place, you need to look up the formula that gives you more digits in order to keep them. But the formulas are very basic, and I assume that by now we've done enough addition and subtraction, or let alone math, at this point, that we're just kind of done with this. So I'm not going to make you do these. We're just going to skip straight to the end. And we'll say that that's good enough. All right. So what I'm going to do is I'm going to, if anybody has any, well, actually, I don't think 10 minutes is going to be enough for us to do any Q&A. What we'll do is this. So if you've been using the class Discord and you have questions that you want to ask me about homework this week, take a photograph and upload it to the class Discord channel. And then I'll be here this afternoon, and I can answer your questions this afternoon and this evening. I do have something I need to go to at about 5 p.m. But after that, I have the evening free, and I'm happy to answer any questions that you have over Discord or email. And if you're not in the class Discord, where are you? We miss you. Come join us. All right, so that is it for Unit 5. I am missing this thing. I need my outro music. And yeah, so when we come back next week, we're going to do actual chemistry, believe it or not. We're going to start by talking about matter, and then we're going to work with some basic, like, what's the structure of the atom, etc. stuff. So that's going to be Units 6 and 7. There is a quiz for Units 4/5/6. So you're not going to get a second quiz piled on top of your first quiz just yet. But those days are coming. They do kind of rack up pretty quickly, so be mindful of that. The third quiz will come up sometime next week. But other than that, make sure you get lab number 1 in. It's due tomorrow. Closes on Thursday. I don't know why the audio balance is way off. Hold on. What did I do? My headphones are being stupid. That's fine. I'll fix it later. I don't know if it's only playing out of the left ear for you guys, but whatever. Alright. Yeah, have a good one, and I'll see you next week. Take care.